Math 1332, Chapter 2, Set Theory, Section 2.2, Subsets and Set Operations, Video 2, Subsets and Proper Subsets. In this video, we're going to define sets, subsets, and proper subsets, so let's get right to it. All right. Let's start with the definition of a subset. If A and B are two sets, now I did mention that they're contained in some universal set U, but the truth is we don't have to make reference to a universal set when defining subsets, but they do exist in some universal set. So if A and B are two sets, then we say A is a subset of B if every element of A is also an element of B. Now, before we go any further, let's think about what this means. Let's go back to an example that we used in the previous video about having all the citizens of the United States in a room. If all the citizens of the United States were in a room, then wouldn't all the citizens of Texas also be in that room? They would be, meaning that every citizen of Texas is also an element of the citizens of the United States. So we could say that the citizens of Texas is a subset of the citizens of the United States. You can almost think of a subset and a set as one box inside of another. For example, let's say we have this box here, and these are all the US citizens. So it's a really big box, and everybody lives inside of there. But inside of that box, there's another box. I'll just put a little dot there. And that is the box of all Texas citizens. The pink box containing Texas citizens would have to be inside the black box containing US citizens because all Texas citizens are US citizens. That means that Texas citizens is a subset of US citizens. Could we say it the other way around? Could we say US citizens are a subset of Texas citizens? We could not, because not all US citizens are also Texas citizens. If you're a citizen of, say, Utah, then you're not a citizen of Texas. But since all Texas citizens are also US citizens, we could say that Texas citizens is a subset of US citizens. As far as a proper subset, it's pretty much the same definition with one catch. If A is a subset of B, so we're already starting with one set being contained inside of another. But, and you'll have to forgive me, I forgot to draw something here. One second. But A is not equal to B, then we say that A is a proper subset of B. Emphasis on the word proper. As soon as I can get it to draw. Underline the words we're defining. So if one set is contained inside of another, then that's called a subset. But if the smaller set is actually not equal to the larger set, then we say it's a proper subset. So what are examples of improper subsets? Well, the set of all US citizens is not a proper subset of itself. It's a subset of itself, but it's not a proper subset of itself because the two sets are equal. There is a notation, a symbolic notation, to represent these relationships. The way to represent A as a subset of B is with what looks like a sideways U with a line under it. And this would just be read, literally, A is a subset of B. It's almost like a less than or equal to symbol. It's not, but it kind of looks like a less than or equal to symbol. Just round instead of pointy. The symbol for A is a proper subset of B, or rather I should say the notation, looks exactly the same except it does not have the extra line underneath. So unfortunately, these symbols look very similar with the exception of the line underneath. But there's a real easy way to remember which one is subset and which one is proper subset, as long as you remember that a proper subset does not allow equality. And the trick is to remember these two symbols. which you should be familiar with. This one is less than or equal to. It allows numbers to be equal. This one is just less than. It's called a strict inequality. It doesn't allow numbers to be equal. So the only difference between these two symbols is that on the top one, if the numbers are equal, then that's true. 5 is less than or equal to 5. But on the bottom one, it would be false because 5 is not less than 5. So the one with the line underneath allows the things on both sides to be equal. But if it's missing the line underneath, then it does not allow them to be equal. So the one with the line underneath, it's okay if the sets are the same, but the one without the line underneath, it's not okay if they're the same. So the little line underneath is like half of an equal sign. All right, this is cute in theory and all, but let's take a look at some examples. Determine if each statement is true or false. So the good news is these are binary questions, meaning that technically you could guess and get a 50% chance, but I want you to have a 100% chance of getting it right. Let's start with example A. The set containing 1, 3, and 5 is a subset of the set containing 1, 2, 3, ellipses, 10. In order to be a subset, every element of the first set must also be an element of the second set. That's what this definition says. In order to be a subset, every element of the first set is also an element of the second set. Let's highlight that in a different color. Every element of the first set is also an element of the second set. So we have to pass judgment on every element of the first set and ask it a question. So let's do that here. Excuse me, number 1, are you an element of the second set? Yes, I am. So he's okay. Excuse me, number 3, are you an element of the next set? Yes, I am. So he's okay. But it has to be true for everyone. Excuse me, number 5, are you an element of the second set? Well, although it's not explicitly listed, the ellipses kind of imply that the pattern continues, and the pattern being 1, 2, 3 would continue with 4 and 5. So all 3 elements of the first set are also elements of the second set, with the third element being implied by the ellipses. Since everything in the first set belongs to the second set, that makes this statement true. The first set is a subset of the second set. Let's take a look at the second example. The set containing A, B, and C is a subset of the set containing A, B, and C. Remember, with the line underneath, it means subset of. Without the line like this one, it means proper subset of. Again, this may be easy to see. Yeah, everything in the first set belongs to the second set, but you can process it at the element level, one element at a time. So let's just do it real quick, one element at a time. Excuse me, A, are you in the second set? Yep. B, are you in the second set? Yep. C, are you in the second set? Yes, I am. Since every element of the first set is also in the second set, that means the first set is a subset of the second. That is true. Now, if you're questioning, but those sets are equal, I mean, just look at them. This set contains A, B, and C. This set contains A, B, and C. Then that's a good thing to be worried about, but when you're talking about just subsets, it has no stipulation about the sets not being equal. It's only proper subset that has the stipulation of the sets not being equal. Speaking of which, let's look at C. The set A containing A, B, and C is a proper subset of the set containing A, B, and C. The definition of proper subset requires 2 things. First, you have to be a subset, and secondly, you can't be equal. So it's like a follow-up. So how would we think about this one? Notice the first set is a subset of the second set. We just did that in example B, but they are equal. Since proper subsets cannot be equal, this statement is false. So no, the set ABC is not a proper subset of itself, because no set is a proper subset of itself. In fact, that would be a good follow-up. No set can be a proper subset of itself. But you know what? If we're going to make this follow-up here, that no set can be a proper subset of itself, maybe we should go back to example B and draw a similar conclusion. Because if you notice in example B, the sets are actually equal. This set is the same as that set. Well, it should seem pretty obvious, but every set is a subset of itself, just not a proper subset of itself. So let's go ahead and make that observation here. In fact, every set, I think every should be in caps. Every set is a subset of itself. Because remember, the criteria is you check each element in the first set, does it belong to the second set? But if the sets are equal, then yeah, they have to be subsets. All right, let's take a look at D. The set containing 2, 3, 5, and 7 is a subset of O. And remember that O was the set of odd natural numbers, so that's probably worth stating here. Recall that O is the odd natural numbers. And we can list them out, but I don't think there's a need to. We all know what odd numbers look like. Not sure we got the parentheses there because it's supposed to be an O. There we go. Recall that O is the odd natural numbers. So let's go one element at a time and ask it the question we need to ask it, which is, do you belong to the larger set? So let's go to element 2. Element 2, do you belong to the odd numbers? No, you don't. At that point, there's no need to pass any more judgment. We've already found a bad element. The others are okay. 3, are you in here? Yes. 5, are you in here? Yes. 7, are you in here? Yes. Everybody's in there except the 2. And the definition for subset says that every element is an element of the second set. But in this case, 2 is not an odd number. So let's wrap this one up. Since 2 is not an odd number, this statement is false. The statement is saying that every number in the first set belongs to the second, and that's simply not true. Thank you, number 2. If the 2 weren't there, then it would be true. All right, the natural numbers are a proper subset of the whole numbers. Well, this is just checking to see if you remember what the natural numbers and the whole numbers are. We've said it multiple times, and I'm not going to write it this time, but I will say it one more time. The natural numbers are the numbers that you count with, 1, 2, 3, 4, 5, and so on. The whole numbers are those numbers, including the number 0. So the whole numbers go 0, 1, 2, 3, 4, 5. This is really asking, is every natural number also a whole number? And the answer is yes, which means that this statement is true because of what I just said. Every natural number is also a whole number. I can't type today. I can't type most days. So that one is true. Every natural number is also a whole number. But what about the last one? The whole numbers are a proper subset of the natural numbers. First, you check subset. Is every whole number also a natural number? The answer is no. Most of them are, but there's one exception. What is the only whole number that is not a natural number? The answer is 0. This is false. Since 0 is a whole number, but not a natural number, the statement is false. That's all it takes for a subset statement to be false. If you can find one thing in the first set that does not belong to the second. All right, so again, subsets to me is just like one collection of objects inside of another one. And if there's even one exception, then you are not a subset.